Hello, my name is Elon Borgi, as a lot of you probably already know. As you gotten to know me during the class, or I've known you throughout a lot of semesters. This is my final project presentation, kind of like conclusion on what's been going on this whole semester. So getting into it, just kind of review real quick. Yeah, I'm doing the transtibial lower leg prosthetic. Um, and moving forward, I am focusing on the rod of the prosthetic mostly. I do incorporate the spring and the foot in like the fixed joint at the bottom of it, but for the most part, I am focusing on the rod, um, which, and to be fair, is one of the more easier ones to work with, and it kind of allowed me to have a bit of an easier time. Um, and then kind of going over what I was just talking about. I categorized it the three different parts of the prosthetic: the sleeve, the joint, the peg. I will be again focusing on the peg part of it, which I um, will further along will be just referring to it as the rod, because it's makes more sense that way. And so the just skipping that slide, the when I was simplifying this, actually just kind of a review of my progress report. I was looking over a lot of those problems in near the chapter, like I said, chapter 11, and that's kind of how I got the idea for setting up my problem like this. For the horizontal spring representing the torsional spring, and just looking at the perpendicular force for the weight of the patient as they're pressing down, or as it's bending in that motion. And there was a problem in the book that was very similar to this, which helped a lot. And yeah, that's generally why I came up with this. And just like I had said, there's three components. There's the rod, there's the hinge, which is the foot, the joint at the foot where it can bend, not too, and this is the other aspect too, is it doesn't bend fully, like completely free, because if it were to just fully be able to swing back and forth, the foot could catch on the gravel, or the ground, I should say. So it'll only be able to bend as far as it needs to for motion. And then, and yeah, the spring representing the torsional spring, or the horizontal aspect of it. And so getting into the motion, like I did before in the progress report, the motion is going to be like a rotation, and I simplified it by just taking the perpendicular force all the way through, seeing as the other component of the weight from the patient is only going to be compressing the rod, and it wasn't going to be as impactful. Like when I kind of involved it a little bit in some of the calculations I did, it didn't really have much of an impact overall on like deflection and stuff. And so I just I didn't see a need to include it. And yeah, and that's why I chose just focusing on the perpendicular horizontal component of the force. And so this is actually where things actually get the actual components, or not components, but the material of the of the of the of the prosthetic. Actually, it becomes important when we're talking about deflection, because I do need the Young's modulus in order to calculate the deflection. And so again, these are the properties that I found, and I mostly use the Young's modulus, as I just said. And so again, going over some of the calculations I had done before, there's the inertia of the rod from the force, which is pretty self-explanatory. D'Alembert's principle, which I wasn't able to go in as much depth as I wanted to. The chapter 11 didn't explain it as well as I was hoping, or chapter 12. I continued reading through the book to try to get a better understanding of it, but it was pretty difficult. But it really did help to be able to look at things, like I said previously, in from a statics point of view rather than a dynamics point of view. So yeah, overall it did help, like looking over the calculations moving forward. Like it didn't really, I didn't really use that equation as much, but I did do some like calculations for using it as like a governing equation. And then the natural frequency, which was involved in some of the problems, but in the end, it didn't apply as much to what I was doing. And so continuing with the calculations, I did just end up focusing on mostly the deformation of the rod from the forces, as that was a way for me to simulate in ANSYS, which in the case of like the D'Alembert's equation isn't really, you're not able to simulate it as much as I wanted to. So because it's the one we've been using through class, the static structural, didn't really have that the means to which to simulate that type of motion, or that type of equation. And so when I was calculating the total deformation, I created two models, because in the meta study that I was looking at, there was mostly a rod that was like a square rod, like a square cross-sectional rod, and it was mostly what was used there. I mean, there like mostly because the meta study was looking at a lot of older prosthetic legs, but the more current prosthetic legs obviously use more cylindrical rods, because it just has a better means of distributing stress and strain. It doesn't have those sharp corners, and so initially I was going with the square rod, but I did do simulations for both, and so I did calculations for both. I looked at a few different points along the rod, but the one that I focused on just for the presentation here is at the end point, which you'll see here in a moment, which is like called peg, which is kind of like which might be a little confusing. It's basically like a little peg that I put here. I'll show it here in the slide, but it's a little peg that I put at the end of the rod in order to kind of represent generally where the torsional spring connects. And so yeah, this is the square, the cross-sectional, the square cross-sectional area rod, which is the simpler of the two. And so going into the simulation for the total deformation, it did cut like at the end, very end of the peg, it did come out to 0.00, like what was it, 72 inches of deformation, which if you had seen from my calculation, it was about point point 0.0142, which is, you know, roughly like double. And so it was close, but it obviously wasn't exact. And I do take the simulations calculations to be a bit more accurate than the ones that I'd done by hand. And with that, since I was mostly focusing on the deformations, I was still curious about some other simulations. So I did run some others, such as like looking at the maximum principal stress, which kind of was to be expected, where a lot of the tensile stress was going to be on the side that was being bowed, while the inner part was under compression. I mean, it seemed it seemed like that was what was going to be the case. But I just wanted to check for fun. And looking at the strain, obviously, kind of was expected as well. Like the greatest amount of strain was going to be at the fixed point where, or I should say, the point where the the hinge joint comes to a stop, because obviously it's not, again, like I said, it's not completely bending. That was going to be the point where it's where the maximum stress was strain and stress was going to be at. And so for the cylindrical rod, it came out I got a little bit more of an accurate result to, or not accurate result, but I got a little bit more of a similar result to what I had done by hand calculation. And so I was kind of proud that I got a little bit closer with this one. But generally, as you can see, the most amount of deformation happens to be at the top where the forces are at. And also, I would like to point this out because I thought this was a bit interesting. For the square cross-sectional rod, wait, what is it? The total deformation, the maximum of it, generally was distributed along the peg and the top of the rod. While in the case of the cylindrical rod, it was a bit more focused on near the peg, and then kind of when it got to the rod, it got significantly more dispersed. And so I guess that was kind of an indication of why they would be using cylindrical rods a little bit more as well for this application. And so generally the error that I got was at the most around, this is the most error that I got, which is from the square rod, which is about 50% roughly, which generally I kind of see as a as successful. Obviously it's not 100% accurate, but I mean it's kind of difficult to be 100% accurate when you're using like generalized formulas. And so yeah, and that was the end of my project. So thank you so much. And yeah, here's the references. You can again go look at the meta study. I thought it was really interesting. It also had significant amount of like research. You can go into their resources and find a lot of interesting information. I very much enjoyed reading about it. So yeah, thank you.